All right. Let me start with the fact that we don't do things this way to make them harder, especially when we crash and burn on them. But the fact is that you do want to start to learn the most at this point, not necessarily just the easy way. You want to learn the one way that solves many, many problems. And so I'm going to go through here and go through again what we did in class today at the very end. And that is a vector projection of vector 1 onto vector 2. And I'm going to point out once again that these very often have to do with projections and mapping. And so what we did in class today, and we may have misspoke, I might have misspoke that we had point 1 at 0, 0, point 2 at 50, 50, and then point 3 at 50, 0. And so we had basically one vector that went from here to here, and then another vector that went from here to here. Of course, what we really wanted, the discussion was the station and offset of point 3 on the more or less the alignment that's defined by P1 to P2. Now there's a lot more reasons to do this one, but that's the one that basically will come up first for you. And so remember, we wanted to go with the vector of V1 onto V2, right? So they're going to call this V2, and I think that's where I screwed up in class. We're going to call this V1. And so let's think about writing these out. V1 is equal to the list, basically 50, 0, and I'm going to leave it at that, though we know that there's another 0, and V2 is equal to the vector or the list 50, 50. And we knew that the projection, which is just going to get the station, once we get that, we can do some subtraction, because in effect the offset is vector 1 minus the projection of vector 2, vector 1 onto vector 2. And so let's get the projection. Projection is vector 1 dot vector 2, or vector 2 dot vector 1, divided by the magnitude of vector 2 squared times the actual vector 2. And that, of course, equals, and we stack these up, 50 times 50 plus 0 times 50 is 2,500. And the mistake I made in class was that, in fact, this is the square of the distance formula. And this distance formula, of course, is the square root of the change in x squared plus the change in y squared. And when we square the square root, we get rid of that, and we have, in fact, this is what? 2,500 over 5,000 times vector 2, or 1/2 of vector 2, and so that projected vector is, the projected vector is equal to 1/2 times 50, 50, or 25, 25. Now, of course, that is just the projected vector. What we want was the station, so the station equals the square root of 25 squared plus 25 squared. Now, as you go through something like this, every now and then I'll try to move this thing off to the side and say yes, every now and then, and that remembers it. We're going to take 25 squared plus 25 squared, but it's just the length that we're talking about here, and then we're going to take the square root of the answer, or the number in the stack, if you would, and that's, of course, 35.35. And so the station turned out to be 35.35 from the beginning station. Now, as I go through to the next one, let's go through, and we realize that we have a vector here, 25, 25, and another vector that was 50, 0. So I'm going to go ahead and go to a new right? And so here are two vectors now. We have one vector that we know is this one here, right? And we have the other one we know that is this one here. So this vector is 25, 25, and this vector is 50, 0. And what we want is this vector from here to there, or vice versa, because we're just looking for the offset. And so do we have to realize? Well, we have to realize that this vector here is just this vector minus this vector, or the addition of the opposite of the vector. So it is 50, 0 plus or minus 25, 25, or minus 25, minus 25. And so we have that vector that essentially goes from here to there, being equal to be 25, minus 25. And in fact, what that vector shows is it's this vector going from here to there. And so in fact that we now know, we just did that before, that the length of that vector is the square root of 25 squared plus 25 squared, which of course is that same number up here of 35, 35. And so our station offset is in fact, I'm going to go forward here, station offset is in fact 35.35 and then 35.35 right. Now, it came up in a nice discussion that why are we doing this? It's too hard, or this is the hard way. And yeah, sometimes it seems that way, and maybe it is. But the fact is, these problems are then designed to work in 3D. Vectors are about 3D, 4D, 5D, 6D. And we probably won't go anywhere beyond 3D, but let's look at what the problem could have been. Problem could have been that your first point here, I'll leave it, was at 0, 0, 0, and your second point was at 50, 50, 36. And maybe your other point was maybe at something like 50, 0, 27. And what you would wanted to get was the projected vector onto there, and then how far off that was to the projected vector. That's basically an intercept path, trying to figure out how to get from here to there most efficiently. And so what would be the mathematics? Well, once again, the mathematics would be the same. This would be V2 and this is V1, and it would be the same. It would be V1 dot V2 divided by the magnitude of V2 squared times the actual vector V2. And now your mathematics is very similar as well. The magnitude of the top of this is going to be equal to 50 times 50 plus 36 times 27. So 36, turn this on, 36 times clear, 36 clear, 36 times 27 plus 2500. That is 3472 divided by the magnitude of V2 squared, which in this case, V2 squared is no longer, it's 50 squared plus 50 squared plus 36 squared. So in other words, we have 5,000 plus 36 squared. And then we're going to take second square root of the answer, and we get 79.34, and then we're going to square that. So we're going to take that and square it, and we get, in this case, 6296. So our projected vector is just the same vector 50, 50, 36 times that value. And so you end up with the projected vector in 3D, and then you can go out and do the same thing to get the slope or intercept path from this point back to there. So this vector stuff, just look up vector projection. Hopefully it'll be right down at the bottom of the screen, and maybe you'll find Sal, and Sal will convince you that we do things to be a little bit more durable than just one thing. Thanks for listening.